Storing and querying massive datasets can be time consuming and expensive without the right hardware and infrastructure. BigQuery is an enterprise data warehouse that solves this problem by enabling super fast SQL queries using the processing power of Google's infrastructure. So you can simply move your data into BigQuery and let it handle the hard work. You can control access to both the project and your data based on your business needs, such as giving others the ability to view and query your data. Hello everyone, this is Dhruv from Edureka and I welcome you all to this session where I will be talking about Google's BigQuery. So without any further ado, let's take a look at today's agenda. So we will start this session by first understanding why there is a need for Google's BigQuery and what actually it is. Then we will look at some of its key features and high-level architecture. Moving ahead, we will get an overview of BigQuery's storage as well as techniques of ingesting data into it. Furthermore, we will also look at the different pricing models for BigQuery and try our hands on implementing it practically on Google Cloud Platform. Finally, we will then look at some of its use cases and a case study for it. First, let's understand why did Google release BigQuery and why would you use it instead of a more established solution? So Google BigQuery was designed as a cloud-native data warehouse. It was built to address the needs of data-driven organizations in a cloud-first world. BigQuery is GCP's serverless, highly scalable, and cost-effective cloud data warehouse. It provides both batch and streaming modes to load data. It also allows importing data directly from certain software as a service applications using BigQuery Data Transfer Service. Second, ease of implementation. So building your own is expensive, time consuming, and difficult to scale. With BigQuery, you need to load data first and pay only for what you use. Third, its speed. It processes billions of rows in seconds and handle real-time analysis of streaming data. Now that you have understood why we need BigQuery, let's now understand what actually it is. So BigQuery is a fully managed serverless data warehouse that enables scalable analysis over petabytes of data. It is platform as a service that supports querying using ANSI SQL. It also has built-in machine learning capabilities. So you can build and operationalize machine learning solutions with simple SQL. You can easily and securely share insights within your organizations and beyond as datasets, queries, spreadsheets, and reports. BigQuery allows organizations to capture and analyze data in real time using its powerful streaming ingestion capability so that your insights are always current and it's free for up to 1 terabyte of data analyzed each month and 10 GB of data stored. BigQuery service manages underlying software as well as infrastructure including scalability and high availability. Now let's look at some of the key features of BigQuery. So first of all, it's serverless. So serverless data warehousing gives you the resource you need when you need them. With BigQuery, you can focus on your data and analysis rather than operating and sizing computing resources. So second is petabyte scale. BigQuery is fast and easy to use on data of any size. With BigQuery, you will get great performance on your data while knowing you can scale seamlessly to store and analyze petabytes more without having to buy more capacity. Third is real-time analytics. So BigQuery's high-speed streaming ingestion API provides a powerful foundation for real-time analytics. BigQuery allows you to analyze what's happening now by making your latest business data immediately available for analysis. Fourth is flexible pricing models. So BigQuery enables you to choose the pricing model that best suits you. On-demand pricing lets you pay only for the storage and computation that you use. Flat rate pricing enables high volume users or enterprises to choose a stable monthly cost for analysis. Fifth is automatic high availability. The free data and compute replication in multiple locations means your data is available for query even in the case of extreme failure modes. BigQuery transparently and automatically provides durable, replicated storage and high availability with no extra charge and no additional setup. The sixth one is data encryption and security. You have full control over who has access to the data stored in BigQuery. BigQuery makes it easy to maintain strong security with fine-grained identity and access management with cloud identity and access management, and your data is always encrypted at rest and in transit. Seventh is standard SQL. So BigQuery supports a standard SQL dialect, which is ANSI 2011 complaint, reducing the need for code rewrite and allowing you to take advantage of advanced SQL features. BigQuery provides free ODBC and JDBC drivers to ensure your current application can interact with BigQuery's powerful engine. This is a savage for less knowledgeable people like me who hates learning new stuffs every day. Eighth is foundation for AI. So BigQuery provides a flexible, powerful foundation for machine learning and artificial intelligence. Besides bringing ML to your data with BigQuery ML, integrations with Cloud ML Engine and TensorFlow enable you to train powerful models on structured data. Moreover, BigQuery's ability to transform and analyze data helps you get your data in shape for machine learning. Ninth and the last one is foundations for BI, that is business intelligence. So BigQuery forms the data warehousing backbone for modern BI solutions and enables seamless data integration, transformation, analysis, visualization, and reporting with tools from Google and its technology partners. Let's now deep dive into BigQuery and have an architectural understanding of it. Under the hood, BigQuery employs a vast set of multi-tenant services driven by low-level Google infrastructure technologies like Dremel, Colossus, Jupyter, and Borg. It takes more than just a lot of hardware to make your queries run fast. BigQuery requests are powered by the Dremel query engine, which orchestrates your query by breaking it up into pieces and reassembling the results. Dremel turns your SQL query into an execution tree. The leaves of the tree it calls slots and do the heavy lifting of reading the data from Colossus and doing any computation necessary. The branches of the tree are mixers, which perform the aggregation. In between is Shuffle, which takes advantage of Google's Jupyter network to move data extremely rapidly from one place to another. The mixers and slots are all run by Borg, which doles out hardware resources. Dremel dynamically apportions slots to queries on an as-needed basis, maintaining fairness amongst multiple users who are all querying at once. A single user can get thousands of slots to run their queries. Dremel is widely used at Google, from search to ads, from YouTube to Gmail, so there's great emphasis on continuously making Dremel better. BigQuery users get the benefit of continuous improvements in performance, durability, efficiency, and scalability without downtime and upgrades associated with traditional technologies. Also, BigQuery relies on Colossus, which is Google's latest generation distributed file system. Each Google data center has its own Colossus cluster, and each Colossus cluster has enough disks to get every BigQuery user thousands of dedicated disks at a time. Colossus also handles replication, recovery, and distributed management. Colossus is fast enough to allow BigQuery to provide similar performance to many in-memory databases, but leveraging much cheaper yet highly parallelized, scalable, durable, and performant infrastructure. BigQuery leverages the column input-output storage format and compression algorithm to store data in Colossus in the most optimal way for reading large amounts of structured data. Colossus allows BigQuery users to scale to dozens of petabytes in storage seamlessly without paying the penalty of attaching much more expensive compute resources, typically with most traditional databases. To give you thousands of CPU cores dedicated to processing your tasks, BigQuery takes advantage of Borg, which is Google's large-scale cluster management system. Borg clusters run on dozens of thousands of machines and hundreds of thousands of cores, so your query, which used 3300 CPUs, only used a fraction of the capacity reserved for BigQuery, and BigQuery's capacity is only a fraction of the capacity of a Borg cluster. Borg assigns server resources to jobs. The job in this case is the Dremel cluster. Machines crash, power supplies fail, network switches die, and a myriad of other problems can occur while running a large production data center. Borg routes around it, and the software layer is abstracted. At Google scale, thousands of servers will fail every single day, and Borg protects us from the failures. Someone unplugs a rack in the data center in the middle of running your query, and you will never notice the difference. Besides obvious needs for resource coordination and compute resources, big data workloads are often throttled by networking throughput. Google's Jupyter network can deliver 1 petabit per second of total bisection bandwidth, allowing us to efficiently and quickly distribute large workloads. Jupyter networking infrastructure might be the single biggest differentiator in Google Cloud Platform. It provides enough bandwidth to allow 1 lakh machines to communicate with any other machine at 10 GBs. The network bandwidth needed to run our query would use less than 0.1% of the total capacity of the system. This full duplex bandwidth means that locality within the cluster is not important. If every machine can talk to every other machine at 10 Gbps, racks don't matter. Traditional approaches to separation of storage and compute include keeping data in an object store like Google Cloud Storage or AWS S3 and loading the data on demand to virtual machines. This approach is often more efficient than co-tenant architectures like HDFS, but is subject to local virtual machine and object storage throughput limits. Jupyter allows us to bypass this process entirely and read terabytes of data in seconds directly from storage for every SQL query. In the end, these low-level infrastructure components are combined with several dozen high-level technologies, APIs, and services like Bigtable, Spanner, and Stubby to make one transparent, powerful analytics database, BigQuery. The ultimate value of BigQuery is not in the fact that it gives you incredible computing scale, it's that you are able to leverage this scale for your everyday SQL queries without ever so much as thinking about software, virtual machines, networks, and disks. BigQuery is truly a serverless database, and BigQuery's simplicity allows customers with dozens of petabytes to have a nearly identical experience as its free tier customers. Now that we have reviewed the high-level architecture of BigQuery, we now need to look at the BigQuery storage organizations and format. Let's dive right into it. In this, first let's understand BigQuery resource model. BigQuery organizes data tables into units called datasets. These datasets are scoped to your GCP project. These multiple scopes, project, dataset, and table helps you structure your information logically. You can use multiple datasets to separate tables pertaining to different analytical domains, and you can use project level scoping to isolate datasets from each other according to your business needs. So in this, the first one are projects. So projects are root namespaces for objects which contain multiple datasets, jobs, access, control lists, and IAM roles. It also control billing, users, and user privileges. Second is datasets, which is a collection of related tables or views together with labels and descriptions. It allows access control at dataset level and define location of data that is multi-regional or regional. That is like if it is multi-regional, it can have like US or European Union or any other multi-regions. And if it is just or like regional, so it can be like Asia Northeast. It specifically goes into region, right? So that's how. Then there are tables, so which are collections of columns and rows stored in managed storage and defined by a schema with strongly typed columns of values and also allow access control at table level and column level. The next is views, so which are virtual tables defined by a SQL query and it allows access control at view level. And the last one is jobs. These are actions run by BigQuery on your behalf, like load data, export data, copy data, or query data. Jobs are like executed asynchronously. The next in this we have is storage management. Now let's review how BigQuery manages the storage that holds your data. Traditional relational databases like MySQL store data row by row, means record-oriented storage. This makes them good at transactional updates and OLTP, means online transaction processing use cases. Then we have is BigQuery. BigQuery, on the other hand, uses columnar storage where each column is stored in a separate file block. This makes BigQuery an ideal solution for OLAP, means online analytical processing use cases. You can stream data easily to BigQuery tables and update or delete existing values. BigQuery supports mutations without limits, mutations like insert, update, merge, or delete. BigQuery uses variations and advancements on columnar storage. Internally, BigQuery stores data in a proprietary column format called capacitor, which has a number of benefits for data warehouse workloads. BigQuery uses a proprietary format because the storage engine can evolve in tandem with the query engine, which takes advantage of deep knowledge of the data layout to optimize query execution. Each column in the table is stored in a separate file block, and all the columns are stored in a single capacitor file, which are compressed and encrypted on disk. BigQuery uses query access patterns to determine the optimal number of physical shards and how data is encoded. The actual persistence layer is provided by Google's distributed file system, Colossus, where data is automatically compressed, encrypted, replicated, and distributed. Colossus ensures durability using erasure encoding to store redundant chunks of data on multiple physical disks. This is all accomplished without impacting the computing power available for your queries. Separating storage from compute allows you to scale to petabytes in storage seamlessly without requiring additional expensive compute resources. There are a number of other benefits of decoupling compute and storage. You can also take advantage of long-term storage. You can load data into BigQuery at no cost because BigQuery storage costs are based on the amount of data stored, like first 10 GB is free each month, and whether storage is considered active or long-term. If you have a table or partition modified in the last 90 days, it is considered as active storage and incurs a monthly charge for data storage at BigQuery storage rates. If you have a table or partition that is not modified for 90 consecutive days, it is considered long-term storage and the price of storage for that table automatically drops by 50% to the same cost as cloud storage nearline. Discount is applied on per table per partition basis. If you modify the data in the table, the 90 days counter resets. A best practice when optimizing costs is to keep your data in BigQuery. Rather than exporting your older data to another storage option, such as cloud storage, take advantage of BigQuery's long-term storage pricing. This means not having to delete old data or architect or data archival process. Since the data remains in BigQuery, you can also query older data using the same interface at the same cost levels with the same performance characteristics. Let's now learn how to load or ingest data into BigQuery and analyze them. There are multiple ways to load data into BigQuery depending on data sources, data formats, load methods, and use cases, such as first one as batch ingestion, second streaming ingestion, third one we can say as data transfer service. So the first one is batch ingestion. So batch ingestion involves loading large bounded data sets that don't have to be processed in real time. They are typically ingested at specific regular frequencies and all the data arrives at once or not at all. The ingested data is then queried for creating reports or combined with other sources, including real time. BigQuery batch load jobs are free. You only pay for storing and querying the data, but not for loading the data. For batch use cases, cloud storage is the recommended place to land incoming data. It is a durable, highly available, and cost effective object storage service. Loading from cloud storage to BigQuery supports multiple file formats like CSV, JSON, Avro, Paraquet, and ORC. Second one is streaming ingestion. So streaming ingestion supports use cases that require analyzing high volumes of continuously arriving data with near real-time dashboards and queries. Tracking mobile app events is one example of its pattern. The app itself or the servers supporting its backend could record user interactions to an event ingestion system such as Cloud PubSub and stream them into BigQuery using data pipeline tools such as Cloud Dataflow. Or you can go serverless with Cloud Functions for low volume events. You can then analyze this data to determine overall trends such as areas of high interaction or problems and monitor error conditions in real time. BigQuery streaming ingestion allows you to stream your data into BigQuery one record at a time by using the table_data.insertAll method. The API allows uncoordinated inserts from multiple producers. Ingested data is immediately available to query from the streaming buffer within a few seconds of the first streaming insertion. It might take up to 90 minutes for data to be available for copy and export operations, however. One of the common patterns to ingest real-time data on Google Cloud Platform is to read messages from Cloud PubSub topic using Cloud Dataflow pipeline that runs in a streaming mode and writes to BigQuery tables after the required processing is done. The best part with Cloud Dataflow pipeline is you can also reuse the same cloud for both streaming and batch processing, and Google will manage the work of starting, running, and stopping compute resources to process your pipeline in parallel. The best part with Cloud Dataflow Pipeline is you can also reuse the same code for both streaming and batch processing, and Google will manage the work of starting, running, and stopping compute resources to process your pipeline in parallel. This reference architecture, which you can see here, is like this covers use case in much detail. I hope you have understood till now, like Cloud Dataflow and Cloud PubSub, how and what is cloud storage, how it does it work for making a pipeline through Cloud Dataflow, right? So please note that you have options beyond Cloud Dataflow to stream data to BigQuery. For example, you can write streaming pipelines in Apache Spark and run on a Hadoop cluster such as Cloud Dataproc using Apache Spark BigQuery connector. You can also call the streaming API in any client library to stream data into BigQuery. Then the third one is data transfer service. The BigQuery Data Transfer Service (DTS) is a fully managed service to ingest data from Google Software as a Service apps such as Google Ads external cloud storage providers such as Amazon S3 and transferring data from the data warehouse technologies such as Teradata and Amazon Redshift. DTS automates data movement into BigQuery on a scheduled and managed basis. DTS can be used for data backfills to recover from any outages or gaps. Think of data transfer service as an effortless data delivery service to import data from applications to BigQuery. Let's now look at the pricing criteria and models of Google's BigQuery. So BigQuery pricing has two main components. So the first is analysis pricing, which is the cost to process queries, including SQL queries, user-defined functions, scripts, and certain data manipulation languages and data definition language statements that scan tables. Second is storage pricing, which is the cost to store data that you load into BigQuery. Each project that you create has a billing account attached to it. Any charges incurred by BigQuery jobs run in the project are billed to the attached billing account. BigQuery storage charges are also billed to the attached billing account. You can view BigQuery costs and trends by using the Cloud Billing Reports page in the Cloud Console. So let's discuss the first one, that is analysis pricing models. BigQuery offers a choice of two pricing submodels for running queries under this model. So the first one in this is on-demand pricing. With this pricing model, you are charged for the number of bytes processed by each query. The first 1 terabyte of the query data processed per month is free. Second is flat rate pricing. With this pricing model, you purchase slots which are virtual CPUs. When you buy slots, you are buying dedicated processing capacity that you can use to run queries. Slots are available in the following commitments plans. Like flex slots, you commit to an initial 60 seconds. Second is monthly plan, you commit to an initial 30 days. Then there's annual plan where you commit to 365 days. With monthly and annual plans, you receive a lower price in exchange for a longer term capacity commitment. You can combine both models to fit your needs. With on-demand pricing, you pay for what you use. However, your queries run using a shared tool of slots, so performance can vary. With flat rate pricing, you purchase guaranteed capacity with a discounted price for a longer term commitment. Let's briefly understand the first one, that is on-demand analysis pricing. So by default, queries are built using the on-demand pricing model. With on-demand pricing, BigQuery charges for the number of bytes processed. You are charged for the number of bytes processed whether the data is stored in BigQuery or in an external data source such as cloud storage, drive, or cloud bigtable. On-demand pricing is based solely on usage. So this is how the on-demand pricing structure looks like. You can see like queries on demand are there. Then they are charged for $5 per TB. The first 1 TB month is free. And if you pay in a currency other than like US dollars, the price is listed in your currency on cloud platform SKUs apply. Like here you can see the SKUs, like how you need to choose your currency, and you can filter it by product SKU name or SKU ID or service region or service. Okay. Now let's discuss the second one briefly, that is flat rate pricing, which is also available for high volume customers that prefer a stable monthly cost. BigQuery offers flat rate pricing for customers who prefer a stable cost for queries rather than paying the on-demand price per terabyte of data processed. To enable flat rate pricing, use BigQuery reservations. When you enroll in flat rate pricing, you purchase dedicated query processing capacity measured in BigQuery slots. Your queries consume the capacity and you are not billed for bytes processed. If your capacity demands exceeded your committed capacity, BigQuery will queue up slots and you will not be charged additional fees. So there are flex slots which have like short-term commitments. So flex slots are spatial commitment type. So commitment duration is only 60 seconds. You can cancel flex slots anytime thereafter. You are charged only for the seconds your commitment was deployed. So flex slots are subjects to capacity availability. When you attempt to purchase flex slots, success of this purchase is not guaranteed. However, once your commitment purchase is successful, your capacity is guaranteed until you cancel it. The following table shows the cost of your flex slot commitment. Here you can see like how it hourly cost. You can see like $4 for number of slots 100, and monthly charge is 2920 US dollars based on average of 730 hours per month. Then there are monthly flat rate commitments. Following table shows the cost of your monthly slot commitment. You can see like $2,000 it is given for 100 slots. Then there's also annual flat rate commitments. The following table you can see here, which shows the cost of your annual slot commitment. With you can see like monthly cost it's $1,700. only for number of slots 100. All this for US and it's for multi-region. Okay. Let's now move on to the second major pricing category, that is storage pricing. So storage pricing is the cost to store data that you load into BigQuery. You pay for active storage and long-term storage. So active storage includes any table or table partition that has been modified in the last 90 days. And long-term storage includes any table or table partition that has not been modified for 90 consecutive days. The price for storage for that table automatically drops by approximately 50%. There is no difference in performance, durability, or availability between active and long-term storage. Here you can see like the first 10 GB of storage per month is free, and operation you can select like if it's active storage or long-term storage. Then pricing is given for like per GB pricing is given. Like you can see for active storage it is $0.020 per GB, and for long-term storage it is $0.010 per GB. So that's how you can see like for long-term like how the price is saved. And in both of them you can see like the first 10 GB is free each month. Now that you have a theoretical and architectural understanding of Google BigQuery service, let's now see a practical implementation it by trying our hands on running it on Google Cloud Platform. So you can just go to Google Cloud Platform console. We are at console now. So I already have a Google Cloud Platform account. So if you don't have one, create one. It's a very good platform to have your account on. Also, you have to give your credit or debit card details. It will debit 1 rupee and that will also be refunded instantly. And you will get $300 free credit for 90 days. And you can use that credit for like the demo I'm showing you, you can use for that also and for using various other services on Google Cloud Platform. You can see like my free trial is over, but still like what the demo I'm going to show you, it doesn't cost anything. So yeah, let's start. So you can go to BigQuery. So Google BigQuery, you will find it under Big Data Services. So let's see Big Data. Yeah, here's Big Data, and this is BigQuery. Let's open it. So what you have to do is you have to create a data set. So you can just click here, and you can create a data set from here. That's a project name you can say, and under that we are creating a data set. So you can give a name for data set like dataset ID. So you can give it like demo underscore BigQuery. Create data set, and then create a table in it. Yeah, here's the option. Click on this dataset created, then create table. So by clicking here, so yeah, everything is given. This project name, data set name, project name. Yeah, this project name is different. Okay, I will show you just a second. So this is the first step. I have to create a project from here, and it's a Google Cloud Platform project. Like I have demo name project. I have different other projects also. You can create a new project from here. Okay, then only start with BigQuery. Okay, so you can create table under the dataset. So this is the project name demo, and then dataset name demo underscore BQ means BigQuery. Then the table name we can give like what we are going to do today is we are going to import a public dataset named Stack Overflow. I hope you might be knowing about this Stack Overflow website, which have all the technologies like the questions are posted and answers are given to that, like people do engage in that. So what we are going to find out is in last decade, like which technology has been posted the most, means the questions are being posted the most related to which technology. Okay, so you can just give it a name, table name like top underscore. We are going to find the top 10 technologies. So top underscore 10 underscore tech. We can give create a table in it. So yeah, table is being created. So here it is. Inside the project we have demo. In the demo we have top 10 technologies. Okay. Now what we have to do is we have to add data. So we can go here, add data. You can pin a project or you can insert a data set if you have an external data set, a very big or like very small or big, it depends on you. Okay, what kind of data set you want to work. But right now we are going with public data set, so we can just import a public data set. There are various data sets provided here, you can see. So you can see the latest one is about the COVID-19 public data set, where you have all the information about the patients and the how the cases are increasing and how the infected cases are increasing, or if they are going down, whatever the analytics is there regarding all the statistics and analytics, whatever is provided with the data of the COVID-19, all those are provided here. In which state or which country wise, all those data are provided here. Okay. So, but we are going with Stack Overflow, so we will just type here Stack Overflow. Yeah, here it is. So you can see all overview is given like what Stack Overflow is the largest online community for programmers to learn, share their knowledge and advance their careers. We know all these things. Okay.
Then there are samples like here are many examples of SQL queries you can run on the data. These are just the samples which are given, the questions posted and the answer, and all these things are there. Now we have to do is view the data set. It will take us to another BigQuery window, back to the query page. So yeah, so we are here now. The data set is being imported. Stack Overflow is here. So we can just go into Stack Overflow, and if you open it, there are certain tables are there, like badges, commands, post links. There are multiple tables are there, but we have to go for the questions, like how many times the questions is posted. So we will choose this table name, post questions. So as you open this, let's extend this a little. Yeah. So if you see this, first of all, the schema will be shown for the table. Like you can see, like the features are given, like the column names. You can say column names of features. You can say it. So all these features are given, and their data types are given, and they are like nullable or it's not nullable. Everything is given. Okay. Then there are the details of the data set. You can see like the size of the data set is like really huge. It's not small in any sense. 33.14 GB is a lot, and there are like you can see number of rows, like 20 million rows are there. Then you can see the date for it, like date it's got created on, last modified, and every data location, everything is given here. And then you can see the preview also. What does these column features name actually? Okay, so just a second. Preview the size. So you can see everything is given, body and everything, like except answer ID, comment account. These are all the features. Okay, the column names. But the most important is the text. So we have this text. You can see the data explorer. The view count for data explorer keyword is 2. So in that way, we have to write a query for it to find out the top 10 technologies. Okay. So let's start. So what we have to do is we have to query the table first. Now what we have to do is we have to select. So let's split tags. We have to split first the tags. So working on this tag column. So we have to split the tags from query product. All this limit we can remove from here. 10,000 limit is given, so that we can remove. And then we can give like from where we have to extract it. So like if there is any date column is given, so because we are finding for the last decade, right? So we find from the creation date. Okay, there is this creation date, so we have to extract from the year. We want to extract only the from the year, so we are just choosing the year here. Here from creation date we are extract creation date. We have to give the flattened text also, so we have to select the flattened text. So you can choose it from here, select tags, and then we can choose the tag count. So tag underscore count, and then we will join it below. Okay, from creation date we have to give, so that's the problem. Now it won't be flattened tags. Now we can just cross join it. So cross join, you can use the unnest for it. So we will join the text with flattened joins, so that works out like a self join, you can say. So tags can group by flattened text, so we have to group by, and then we have to order by tag count in descending, because we need the keyword with the technology name with the maximum count, so that will come first if we order by descending order. So descending, then we'll limit it to 10 because we want the top 10, right? So limit 10. Now it can be done. So the query will process 703.9 MB it is showing, so we can just run the query. Now you can see all the queries are here now, like all the technologies are given. So you can see like the JavaScript is topping the list. So then there's Java, then there's Python. You can see like there are 21. So you can see like 21 means I would say like 2.1 million counts are there, tag counts are there. CSS at 10, C++ at 9. Last decade you can see their tag counts, like how many times they are searched. So we are successful here. Now we can see the job information is given, everything is given. So what we can do is we can just save this, save results. Okay, you have to save this in a table, like the table we have created. You can also save it as CSV or JSON file and everything, like Google Sheets also, but we will save it as BigQuery table. So table name was job underscore 10 underscore tech, saved as a table. So now you can see like job history one running to show the job history, like it has been created, the table has been created, like the result is being saved as a table, so that table has been successful. So now we can see, if you go here the project, we have this data set, then we have this tag. Yeah, so You can see the details for it, like patent tax and tag count are there in the table. Then we can see the details like 148 byte, it takes total space, table size. Then preview, if you see like this table is saved here. Okay. Before saving the view, let's understand this. Like you can also share this table, or you can copy the table and delete table, or you can like export it to Data Studio, like export with Data Studio, and also you can like export it to Google Cloud Storage also. All these things you can do, and then you can like save view also. If you save this view, like it shows on the view like how the table is working and how output it shows, everything that can be done. And then you can schedule the query, how you want to run it, weekly or daily or monthly, however you want to schedule it. You can schedule it that way. Okay. And then there is like you can also do the query settings. So query engine you can choose for it, like Cloud Data Flow, BigQuery engine. And also if you are like querying it and if you forgot to save it, yeah, it can get saved in a temporary table. That temporary table you can create it from here. Okay, you can see here in that after this, like all these things have been there, job priority, everything, and destination table with preference, all the things you can choose. One more cool feature I want to show you, and that can show you only if I run the query again. So let's run this query again. So come down to execution details. What you can see here is how your queries are further split into multiple queries to get the results. So first thing is you can say these are like the working nodes, which is like a different concept of another different concept of Hadoop file system or Google file system to discuss about. But that's how it divides into multiple queries. So here you can see like first how it's wait, read, and compute and write, everything is being divided. And then you can see like first thing was like there are 20 million rows. Okay, first step in input. And then when it comes to sorting, it decreases down to 20 million to it decreases down to 2 million rows. And then finally when the output comes, you can see it been reduced down to 130. Okay, in the final stage when you have ordered by descending order everything, and when you limit it to 10, it comes down to top 10 technologies, right? So this is how it's been done. I hope you have understood it now. You can see how everything it provides at the dashboard. Only everything is, every service, it doesn't take time. That's the thing about BigQuery, that it's very fast. Let's now understand some of the use cases for BigQuery. So the first one is migrating data warehouses to BigQuery. So you can like solve for today's analytics demands and seamlessly scale your business by moving to Google Cloud's modern data warehouse. Streamline also, you can like streamline in the sense you can also streamline migration path from Netezza or Oracle Redshift, Teradata or Snowflake to BigQuery and accelerate your time to insights. You can like also streamline your migration path from Netezza, Oracle, Redshift, Teradata, or Snowflake to BigQuery and accelerate your time to insights. And the second use case is predictive analytics. So predictive analytics helps you predict future outcomes more accurately and discover opportunities in your business. So the Google's smart analytics means BigQuery's Google BigQuery's smart analytics reference patterns are designed to reduce time to value for common analytics use cases with small code and technical reference guides. You can like learn how BigQuery and BigQuery machine learning can help you build an e-commerce recommendation system, but also like predict customers and lifetime value and design propensity to purchase solutions. Also, you can bring any data into BigQuery, make analytics easier by bringing together data from multiple sources in BigQuery for seamless analysis. You can upload data files from local sources, Google Drive or cloud storage buckets, take advantages of BigQuery data transfer service, data fusion plugins, or we can say like leverage Google's industry leading data integration partnerships. You have ultimate flexibility in how you bring data into your data warehouse. Let's now see a case study for Google BigQuery. It's the final topic we are discussing. Then we will wrap up. So, Safari Books Online uses BigQuery to solve a few key challenges, like building detailed business dashboards to spot trends and manage abuse, improve sales team effectiveness through sales intelligence, and enable ad hoc querying to answer specific business questions. So all these things we will understand step by step. So what they did is, means the Safari, what they did is they choose BigQuery over other technologies because of the speed of querying using a familiar SQL-like language and the lack of required maintenance. So Safari Books Online has a large and diverse customer base constantly searching for accessing a growing library of over 30,000 books and videos from an increasing array of the desktop and mobile devices. This activity stream contains powerful knowledge which we can use to improve our services and increase profitability. Locked up in the mountains of usage data are trends such as top users, top titles, and connecting the dots for sales inquiries. Safari's usage data was much too massive to query online in its entirety with the previous toolset. Analysis could be done with the third-party web analytics tools such as
omniture, but those tools lacked the ability to query and explore record level data in real time. In addition, they didn't have a great backend for developing visualizations. SQL like querying had to be done on smaller chunks of the data and was labor intensive and slow. They were impatient waiting for MySQL queries to finish and were often in doubt or as to like whether or not they should finish at all. Once you reach a database client timeouts of 10 minutes, you are in the realm of not being able to do like ad hoc analysis. Answering operational questions can be like time sensitive, so speed is important. Of course, it's very important. So we played with Hadoop, but we in the sense, I mean, Safari organization has actually like played with Hadoop, but it proved to take a lot of resources to maintain. So they ended up putting it on the back burner for future projects. Then they learned about Google BigQuery through a video from Google Input and Output determined it seemed perfect for their use case, so they decided to try it out. So first step is like you can see here this diagram. This tells you how Safari get the data into BigQuery. So no matter what database platform you use, the extract, transform, load step can be a challenge depending on your data sources. BigQuery is no exception, I would say. Then this diagram shows an overview of how the data flowed through the landing and ETL servers leading up to BigQuery. The usage data comes from content delivery networks, means CDN, and web application server logs. This data was packaged into time-based batched chunks automatically copied into a landing directory. It needed some transformation to load into BigQuery in a format where we could get the most use out of it. Here are the basic steps Safari went through. So it got a list of all source files they have previously loaded into BigQuery. Then validate the list of source files waiting to be loaded into BigQuery, then transform the files and copy the files to BigQuery Cloud Storage, then load the files into BigQuery, and finally using the data once it is in BigQuery. So BigQuery proved to be a good platform for dashboard data and offers the capability of drilling into the data in the dashboard further with the BigQuery browser based UI for ad hoc analysis. So here you can see like his dashboard used internally by Safari's operations team to monitor top users. If anything raises any questions, you can get more information about a user, a title, an IP address by querying with the BigQuery browser tool. Now you can see as a dashboard, Safari uses internally to keep an eye on trending top titles. Again, if anything raises any questions in the dashboard, BigQuery can answer them for you. The data is fed to these dashboards by an intermediary schedule job, which is executed via cron. This script queries BigQuery with the BigQuery command line tool, gets the result in JSON, and then contacts some other web services to get more information, which is not stored in BigQuery, such as the user data and book thumbnail images. Then it is all matched up and presented in the dashboard. This is a good pattern as you wouldn't want to query BigQuery every time the dashboard was loaded as it could get expensive. It is best to do the analytical heavy lifting with BigQuery, then store the results in something like a cheap LAMP stack for mass consumption. And then the second advantage that the Safari got through BigQuery is sales intelligence, which is another use case BigQuery was great for, scouring Safari's web logs for leads which came into their sales department. This allowed them to relate a lead to other accounts in their system or gauge the level of interest someone may have in Safari by the number of previous books they had read in the past month on their site. Lead is created in Safari's CRM system, and the BigQuery asynchronously searches through its logs like this. So you can see this in query, like you can see this query written. So the result is written quickly and reattached to the lead recorded, allowing Safari's sales department to gain intelligence and contact the lead without having to wait around the information. This gives them a nice summary of the users. The IP address of the lead has done. While IP address are not perfect identifiers, they are much better than nothing. You can see someone from this leads ID. You can see in usage history this how it is given. So you can see someone from the leads IP address has anonymously viewed user ID 0 to 32 pages of our books, and some other users who have accounts with Safari already are active on that IP. Rather than use the BigQuery command line interface, this use case was better suited for server to server, or we can say auth with OAuth, which is like the authorization tool Google uses. So with the Google API's client library for PHP, this enables them to create web service which matches up with data from different sources and returns the result to their CRM. One of those sources is BigQuery. One amazing testament to the speed of BigQuery is that I didn't even have to implement the web service asynchronously. It returns the results from BigQuery within the timeout period of the web service that the CRM requests. Other use case of Safari which they took advantage of through using BigQuery is pure ad hoc querying, which aren't driven by dashboards but rather specific business questions. When Safari released the Android apps, it was easy to run a query on our usage data, and so on Safari's usage data to see the Android page grouped by day. In the Google BigQuery browser tool, it was easy to export the query results as a CSV file and load them into Google spreadsheets to make a chart. So you can see here how this shows when they release their Android apps. This is the graph, and then here's an example of looking at their top users by number searches during a particular hour of the day. There really is no limit to the kinds of insights you can gain from investigating your data. From an ad hoc perspective, there is a huge sense of power being able to answer any question about your billions of rows and data in seconds. For example, you can find out if that strange traffic on your site is a foreign spam bot or a malicious user. As recommended by Google, they divided their data up into years. You can see this in the table. Normally, this would be a bit of an inconvenience to have to do a union statement between the tables, but BigQuery has a nice shortcut for this. So you can give this shortcut, and what it will do is it will create a union between the tables. So they just stack on as many years back as they need to go into their time shaded tables and union them together, since they have made their schemas the same. At the end of each year, they archive of active tables and start a new one. This is the best of both worlds, as it provides the accessibility of having all your data in one big table with the performance of having them separate as they grow. It will make sense to further share the data into monthly increments instead of yearly. Now, the summary of this case study is like Safari generated meaningful knowledge out of a massive amounts of data in a timely manner, which is a challenge for Safari Books Online, like many businesses needed to solve. Being able to keep on top of trends as they happen, while you can still do something about them instead of month after the fact, is very valuable. This leads to lower abuse problems and top line revenue increases by gathering marketing intelligence on trending topics and collecting lead intelligence to close sales more effectively. So that was a summary of case study. With this, we come to the end of today's session of Google BigQuery. I hope you had a great time learning and understanding about it. And if you have any queries, please feel free to leave them down in the comment section below. Until next time, thank you.